Hello all you problem solvers out there, and welcome to the Solutions and Results presentation for NCPC 2021. So we're going to start with talking about how to solve all of the problems, and then we're going to see the results of the contest. And I'll be monitoring the chat here on YouTube, so if you have any questions about anything I say, just ask a question in chat. There's like a 30-second delay or so it'll take a while before you get the answer back, but I will eventually see your question and respond to it. So, without further ado, let's see who made these problems that you worked on today. The problems were prepared by the following people. We have me, my name is Per Austrin, I was the head of jury. We have Andreas Björklund from Aptus, Paul Grönås Drange from Bergen, Nils Gustafsson from KTH, Antti Laxonen from CSES, Jimmy Mordell from Spotify, and Berger Snorason from University of Iceland. So these 7 people did all the work of preparing these 13 problems that you got in today's problem set. So let's start with the problems from easy to hard. The easiest problem in the set was problem K, not knowledge. And here you were given a list of numbers and then another list of the same numbers, except one number had been removed and the order may have been changed. And the goal was just to figure out what is the missing number in the second list. So this problem can be solved in many different ways. The lists were very small, so there was no need for any special data structure or algorithm that did this efficiently in any way. But for this problem, the most efficient solution is actually also the simplest. So let's see what this is. Let the first list of numbers be called x1 up to xn, and the second list be called y1 up to yn minus 1. Then the missing number is simply the sum of all the x's minus the sum of all the y's. So you just add up all the x numbers, subtract all the y numbers, and whatever is left has to be the missing number. So this is kind of a classic simple trick, which is pretty nice. And so if you haven't seen this trick before, this is like a good takeaway lesson from this simple problem. It's like a nice simple trick, which is can be useful in more complicated settings as well. So this problem was solved incredibly quickly, already after 1 minute of the contest, and after 4 hours, 196 teams had solved it, and most teams had solved it already on their first attempt. So there wasn't really any pitfalls or things you could go wrong with here. So there wasn't anything tricky about this problem. The second easiest problem was problem J, joint Jogjam. So here we had 2 people who from time 0 to time 1 were moving in some straight line segments at constant speed, and we wanted to figure out the maximum distance that these 2 people were at during any point of time of their run. And the answer to this problem is simply the maximum of the distance between the 2 starting points and the distance between the 2 ending points. So, this is the answer, and once you know this, it's very easy to code up. But let us quickly see why this is actually the answer. So again, there's an interesting, nice trick here, which if you haven't seen it before, it's another good takeaway lesson, which is that if we think of everything as view everything from the reference frame of the first runner, we can instead think of that person as being a stationary point at 0, 0, and the second person doing all the running. So we can think of this problem instead as being about one person standing still at 0, 0 and another person running in a straight line segment, and we're asking the same question: at what point what is the maximum distance from the stationary person to this moving person at any point in time? So then we can think of the second person at time t, it's at some position x of t, y of t, which is some linear, the x-coordinate is some linear function in t, and the y-coordinate is some linear function in t. That's what it means to run in a straight line segment. And then the square distance from the first person at 0, 0 to this second person at time t is x of t squared plus y of t squared. So it's x0 plus t x delta squared, y0 plus t y delta squared. And this, like, if you look at this function as a function of t, it's a convex quadratic function in t, which means that it's maximized either at the minimum possible time value or the maximum possible time value. In other words, at the start or at the end. So, like, if you plot this function as a function of t, it's going to look like a parabola, and its maximum value is at one of the two endpoints. So this problem was solved. It took as much as 10 minutes to solve this, maybe because there were other problems that you were solving first, but first solution after 10 minutes, and in total at the 4-hour mark, 189 teams had already solved this problem, with, again, pretty few wrong submissions, so there wasn't really anything tricky here. You just implemented this. Moving on to the next problem, problem L. Here we had a pair of cicada species which appears every A and B years, and they were last observed in year Y, and the goal was to figure out the next year that these species will appear together again. And like one simple solution here is just to brute force to try all possible answers until it's found. So you just go from try each year z from like y plus 1, y plus 2, y plus 3 and upwards, and then you check if the difference between z and y is divisible by both a and b, and you break when the first such z is found, because that's the first year when they reappear. So this goes on for at most a times b steps, because once you have gotten like a times b years into the future, you have definitely gotten to a number which divides both a and b. So this is going to end up taking a times b time, which was fast enough for this problem because these numbers a and b were very small. So this is like the naive solution, which is perfectly fine for this problem. There is a faster solution, which is that to note that the joint period of these two species is going to be the least common multiple of the numbers a and b. And if you're unfamiliar with least common multiples, this is a Wikipedia link that you will be able to click once these slides are posted on the webpage, where you can read about what the least common multiple is. And the answer is simply y plus the least common multiple of a and b. And this is a much faster way to compute the answer. It takes only logarithmic time in a times b as opposed to a times b time. So if a and b were very large, this would have been the way to do it, but now it didn't really matter. You could do it whichever way you liked. So this problem was solved super quickly, 2 minutes into the contest, and at the 4-hour mark there were 185 accepted solutions. So slightly more incorrect solutions here, but still relatively tricky-free problem. Alright, so those were the 3 easiest problems. Moving on to the 4th problem. In problem G, graced grains, we got the 10 circles, up to 10 circles. These circles had a radius of up to 10, and their center points were somewhere in the box between 0 and 10. So the x-coordinate of the center was between 0 and 10, the y-coordinate of the center was between 0 and 10, and the goal was to approximate the area of the union of these circles up to some 10% relative error. So we wanted a number which was at least 90% of the true area and at most 110% of the true area. So the solution, well, one thing you can do is you can compute this area with very high precision very quickly using some numeric integration technique like the trapezoid method or something like this. And it's not too hard, but it's a bit of code to actually write this. And because we're only asking for an approximate answer, there is a much simpler solution to this problem, which is to use sampling, like a Monte Carlo approach. So we'll simply pick R uniformly random points within this square with x coordinate between -10 and 20 and y coordinate between -10 and 20. And we chose this box because this is how big the box is, how large the circles can extend. And then if x out of these R points are inside some circle, we simply estimate the area as x divided by R, the fraction of points that were in the circle, times 30 squared, which is the total area of this box. Okay, so and that's it. We just pick a bunch of random points and we use the fraction of points that were inside some circle as an estimate for the area of their unions. And basically, you can when you're solving this, you can kind of stop here and you just implement this and you try some value of R and hope that it's large enough. But if we want to understand how large does R need to be in order for this to be not have too much estimation error? So, and I won't do the analysis in detail here, but what you can prove is that you expect to see, if you pick R points, you expect to see a relative error which is around 24 divided by square root R for this problem. There is some calculation that leads to this. So if you put R, which is at least 100,000, this starts becoming less than your target error, which was 0.1. And if you put R to be 1,000,000, this is more than enough points. And when you have that many samples, it's extremely unlikely that your error is too large. So kind of straightforward. Is like maybe not obvious to see exactly how many points you need, but you can figure it out with trial and error. You can try something too low and see if it gets wrong answer. Try something too high and see if it's too slow, and then you'll find something that works. But I think but 1,000,000 points is more than enough, and will be fast enough. So this problem was also solved very quickly after 7 minutes, and at the 4-hour mark there were 117 accepted solutions, so significantly less than for the previous 3 problems, but still more than half of the teams had solved this at the 4-hour mark. And here there were also a few more incorrect submissions. I didn't actually look so much at these, so I don't know what were the common mistakes here, but I would assume that things relating to having too large error or sampling too many points are common issues. Moving on to the next problem, A, antenna analysis. This problem was we were given integers x1 up to xn, and we wanted to find for each integer I the maximum value of xi minus xj minus c times I minus j over all j less than or equal to I. So to solve this problem, I like a key observation, or maybe another trick, which is yet another take-home message from this presentation. The key observation is that dropping the absolute values does not increase the answer. So let's look at the simplified problem where we maximize the same expression, but instead of taking absolute values of these differences, we just take their differences. So we maximize xi minus xj minus c times I minus j, which if we rearrange the terms is the same as xi minus c times I plus minus xj plus c times j. Just rearranging these terms. Okay, but trying to maximize this quantity is actually very easy. In order to do that, we just go from left to right and we keep track of the largest value we have seen so far of minus xj plus c times j, because this is some expression that it only depends on it's something that only depends on j. So we keep track of the largest value we have seen of this expression so far. Let's call it y. And then when we are at some value I, the answer to this simplified problem is simply going to be xi minus c times I, this first part, plus the largest value we have seen so far for the second part, which we called y. So we just go from left to right, keep track of the maximum value so far, and the answer is this thing. So then this was not exactly the problem we wanted to solve, and in order to solve the original problem, we do the same thing again, but we solve but for the variant where instead of looking at xi minus xj, we look at xj minus xi. And we do the same thing, and we take the largest of the two. And this will give the right answer, because if we think about the j that gives that maximizes this thing, that this expression that the problem asks about, that j will either have xj less than xi, and in this case the simplified problem, the first simplified problem, will give the right answer, or that j will have xj greater than xi, and then this second one will give the right answer. And neither of them, because of this key observation, neither of them will give a too large answer. One of them will probably give maybe a too small answer, but one of them will give the right answer. All right, so this is the problem. Like with this key observation and this trick, the problem becomes very easy. But like finding this trick in the first place is not the easiest thing, maybe. And this leads to a time complexity of big O of n. And if you don't find this trick, there are still other solutions that are more complicated that you could do. Using like some balanced search trees or range trees, which leads to some O of n log n times solution. And this is also a possible way to solve the problem, but leads to a more complicated, more to code and more room for errors. And this is another. This key observation is another kind of nice trick that is good to know about, and it's easy, very easy to forget. I have seen it many times, but I always forget it. I have forgotten about it and missed it in two problems like this, including this one, for in the last month or so. So there's a question in chat about why random place rather than nested XY loops of appropriate resolution. So that's another way to solve the problem. You could just make a fine enough grid. This is relating to the circle area estimation problem again. You can just take a fine enough grid and it's going to turn out to work. It's much harder to analyze this, I would say. It's less, but you can work this out, and this is also a way of solving the problem. But yeah, it requires a bit more effort to prove the correctness. So yeah, lots of ways of solving this area estimation problem. Yeah, okay, so that was A, and because this very simple solution exists, it was solved very quickly, already after 4 minutes. But then, as I said, if you know this trick, it's very easy. If you don't know this trick, it's a bit harder. So there were not as many accepted solutions at the 4-hour mark for this one. 88 teams had solved it, and as you can see, there were a lot more incorrect submissions here. And this is probably because a lot of teams mistook it for being easier than it is, because there were so many teams solving it quickly, and then if you didn't know about this trick, you still thought it was easy, and maybe you did something that was running quadratic time or something like this. All right, so let's see then. So that was problem A, and moving on to problem D. deceptive directions. In this problem, we got a grid map, like a maze in the form of a grid with width W and height H. And we also got a shortest sequence of steps to take in this grid to reach some treasure. However, all of the steps had been replaced by the wrong steps. So a north step might have been replaced by west, south, or east. A west step might have been replaced by north, south, or east, and so on. And each replacement was done independently of the others. So sometimes north was replaced by west, maybe sometimes it was replaced by south, and so on. And the goal was to figure out where could the treasure actually be in this map. So here's the solution. The first thing, because this sequence that we get is supposed to be a shortest sequence that reached the treasure, distances in this map are very relevant. So the first thing that one should do is compute the distance from the starting position to every position in the maze using a breadth-first search. So let's call this, for a position P, let's say that d of P is the distance to that position. And then what we want to do is we want to forbid all of the steps that could not possibly have been used by the correct instruction sequence. Like if we think about this as a graph, there are different steps you can take, or edges in this graph corresponding to different steps you could take. So first, if we forbid taking a step from P to Q, if this edge from P to Q, or if going from P to Q is not something you would ever do in a shortest path. And the condition for this is that the distance to Q is not equal to the distance of P plus 1. Whenever the distance of Q equals the distance of P plus 1, then there is some shortest path in the graph that goes to Q via P. And then this step from P to Q could be used in a shortest path. But if these are not equal, then this step could not be used in any shortest path. The second thing we do is we forbid the step from P to Q if going from P to Q would mean taking the same kind of step as the d of qth step in this corrupted instruction sequence. For instance, if the very first step of the sequence we get was a north, then we could not possibly take a north step from the starting point. So then the step from the starting point to the cell just north of the starting point would be a forbidden step, because the distance of the cell just north of the starting point is 1, and the first step of the instruction sequence was north. So we forbid all steps like this. And then what we do is we simply run a breadth-first search again, but we modify it and take into account that these steps are actually forbidden. These steps could not possibly be taken. And then all the locations that we reach, all the positions that we reach that are at the same distance as the total length of the instruction sequence, all these locations are possible treasure locations. And those are exactly all of the possible treasure locations. So that way, just by running these two breadth-first searches, we are able to find all of these locations. So the running time of this ends up being big O of W times H, so just the size of the map. So linear time in the size of the map. And this was solved, took a little while after these first 5 problems, but this one was solved after 38 minutes, and at the 4-hour mark there were 55 accepted submissions. Next we have problem F, Fortune from Folly. So in this problem we were asking about these infinite random binary sequence like x1, x2, x3 of zeros and ones, and each xi, each entry in this sequence equals 1 with probability p independently, and the goal is to figure out the expected first value of I such that among the last n entries up to I, so xi up to xi minus n plus 1, we had at least k many ones. So here's how to solve this. The first basic observation is that at any given point, you don't care about the full history. Like if you think about going step by step in this sequence, at any given point, only the n most recent xi's matter. So let e subscript z1 up to zn be the expected number of steps until we have k1s if the most recent most recent xi values we saw were z1 up to zn. So then if the sum of these zi's is at least k, well then we already see k once. So then this expected value is 0. We don't have to take any more steps until we have k once. And otherwise, if this is not the case, we have to take at least one step. So this expected value is 1, and then when we take one step, we get one new value, which could either be a 1, with probability p it is a 1, and then we're in a state where we have z2 up to zn and a 1. So we drop like if z1 is the oldest thing, the one that was n steps ago, we drop that one, and we instead add put in a 1 here. So it's p times the expected value, the e of z2 up to cn, followed by a 1. And with probability 1 minus p, we see a 0 instead, so we have the value of e z2 up to zn with a 0. Alright, so this thing is just a bunch of linear equations in these 2 to the n many unknowns, e of z1 up to zn. So it's a system of linear equation in 2 to the n unknowns, and n here was something like 6, so this is 64 unknowns in the worst case. And so we can solve this problem using Gaussian elimination, and then the answer that we're looking for is e of 0, 0, 0, 0. Because we can think of the starting point as, we can think of the sequence as extending like backwards in time, and you know, when you start, you just have a bunch of zeros. All right, so this leads to then to a time complexity of big O of 2 to the 3n using a standard Gaussian elimination algorithm, which is cubic in the number of variables. And one implementation note to keep in mind is that you should, when you're dealing with indices like this, which are really bit strings of length n, you should think of them as n-bit numbers. So this kind of operation of shifting things around, it's a very convenient when viewing these as integers, because something taking z2 up to zn and adding a 0 is the same as shifting z down one step and adding this should be a 0 actually. So taking z2 up to zn and adding a bit b is the same as shifting z down one step and then ORing it with a b in the n-1th most significant bit. All right, so that's how to solve this problem, and this one was solved after roughly half an hour, so a bit earlier than the previous problem, but at the 4-hour mark there were significantly fewer solves for it. It was solved by 27 people, or 27 teams. Next problem was problem C, customs controls. So here we got a vertex-weighted graph, and the goal was to color k of the vertices red and n-k of the vertices blue in such a way that every shortest path from 1 to n has a monochromatic edge. So there's not allowed to be any shortest path from 1 to n which is alternating back and forth between red and blue. So that's the problem. So the first step is to figure out what the shortest paths are in the graph from 1 to n. And here we can use Dijkstra's algorithm to find all of the edges that are part of some shortest path from 1 to n. So there are parts of this which are similar to what we did in problem D with the breadth first search. There we also found all of the edges or all of the steps that could be taken in some shortest path, and we can do it with the same principle here after running Dijkstra's algorithm. So we get a bunch of edges which are those that could be used in some shortest path. And then these edges form a directed acyclic graph, because every edge you take in this, every one of these edges you take you further away from the vertex 1. So we can find a topological ordering of all of the vertices in the graph when we have these edges, so that all of these edges go forward. And then what we do is we color the first k of these vertices red and the remaining n minus k ones blue. So why is this a good idea? So if we look at a shortest path from 1 to n, because we set it up like this, any shortest path from 1 to n can now only switch between red and blue a single time, because it's going forward in this topological ordering, and we make the first few things red. So it's going to start with red, and then at some point it's going to switch over to blue, but then it's never going to be able to go back to red. So it's only going to switch between red and blue once. So any shortest path that uses 3 or more vertices must have a monochromatic edge if we color the vertices like this. So great. That almost solves the problem. The only remaining little thing is that what if there are shortest paths that have only 2 vertices? And what does this mean? This means that there is a direct edge from vertex 1 to vertex n. In this case, because the graph is vertex weighted, this edge from 1 to n must be the only shortest path in the graph. Because going a detour through some other vertices will just make the length of the path larger. This is where we use this fact that the graph was actually vertex weighted. So the only thing we need to do is to make sure that 1 and n get the same color, and then it doesn't matter how we color the rest of the vertices in this case. And this is always possible. The only exception is if n equals 2 and k equals 1. And this was given in the sample input as an impossible case, and this is actually the only impossible case in the whole problem. So let's see, there are some questions in chat about there are many different ways of solving this. It's probably also possible to maybe not use the weights at all. That might be due to the test data being weak. I'm not sure. But there are definitely other ways of solving this. This is like the most elegant solution, using the topological ordering like this. I had a more complicated solution to this problem when I first solved it that did something with looking at the neighborhood of 1 and n. But there are many ways of solving this for sure. So this problem, it took a while to be solved, even though there are so many solutions for it. The first solution came in only after 1 hour and 39 minutes, and at the 4-hour mark there were 15 accepted solutions. Okay, moving on, we're slowly getting to the hard end of the problem set. We had problem H, where we were given some productivity values, Li and Fi, of some n coders. And we got the productivity LF of some consultant, how productive they would be for a T-hour long project. And what we wanted to know whether there is some weighted average of these n coders, such that their average L value is at least L over T, and their average F value was at least F over T. And we were supposed to handle a lot of queries like this, which were then interleaved with some of these encoders leaving and not being available anymore. Okay. So the first thing to do with this problem is to reformulate it a bit and view it more geometrically. So these coders, these Li, Fi, they're really a set of points in 2 dimensions. So we have some L1, F1, L2, F2, L3, F3, where we put L on the x-axis and F on the y-axis. And then this consultant query, this L over T, F over T, is another point in 2D, which is somewhere. And then the observation that you have to make is that this weighted average that we're asking about here exists if and only if this point, this query point, is below this upper side of the convex hull of these points. So we think of these points as we look at the upper envelope of these of the hull of these points, and if the query point is inside here, then there is such a weighted average. So, and then like some coder leaving corresponds to some of these points that were used being removed, which leads to the convex hull possibly changing. So in this setting, this query point is inside the hull. If this coder up here is leaving, the convex hull becomes this thing got added to the hull, and now this thing is out. Now this query point is outside the hull. Right. So like this is the correct way to view this problem it's really a geometry problem. So the problem is really we have a set of points x, y, and we want to maintain this upper side of its convex hull, and we have to support removal of points, and we have to then be able to answer queries about whether some other points, x star, y star, are like below or inside this hull. So here's how to solve it. This hull, this upper side of the hull is a piecewise linear function, so it's convenient to represent it as a sorted set of points, like x1, y1 up to some xt, yt, where t is the number of points in the hull. And you keep them, you have them sorted so that x1 is less than x2 is less than xt, and also y1 is larger than y2, larger than yt. So it's sorted in ascending order by x and descending order by y. The hull will always look like this. It will always be a decreasing function like this. And to answer a query, some query x star, y star, we kind of just have to find like the index I such that x star is between xi minus 1 and xi. And then we need to check if x star, y star is below this line from the I minus 1th point of the hull to the ith point of the hull. And if it is below that line, then x star, y star is within the hull. And there are some like special cases you have to look at a little bit what happens if it's at the endpoints, if it's to the left of x1 or to the right of xt, but it's easy to work out what to do in those cases. So then we have to handle the removals, and there are ways to maintain this data structure under removal of points, but it's a little bit messy, and it's actually a lot easier to handle additions. And here we don't have to solve all the queries in order. We could, because we get all the queries in the input, we can choose to instead run all these events in reverse order, and then the removals become additions, which are actually easier to handle. So we slightly reformulate the problem even further to talk about now additions of points instead of removals of points. So how to handle these additions? Here is one way of doing it. If the point that we want to add is outside the current hull, then we need to add it to our current set of points at the correct position, maintaining this sorted order. And then we have to remove basically any concavities that are formed to the left and to the right of a new point. And the way you do this is similar to how you would do it in a standard convex hull algorithm. So if you've ever implemented convex hull, There's nothing. You're just doing the same thing as you would do there, but you'll have to do it both to the left and to the right of the new point you added. One possible issue here is that like adding a point in this way could in principle take a very long time, because there could be a lot of old points that were suddenly discarded all at once from the hull, and the running time this takes is proportional to how many points you have to remove from the hull to fix the hull when doing this. And so this may seem like an issue, but it's really not an issue, because once a point is discarded, it can never be added back. It's gone forever. So the total number of removals for all of these events is going to be at most n. So amortized over when you run through the whole thing, the total time complexity is going to be n plus the number of events times log n. So this was solved also around the 1.5 hour mark at 1:42. 7 teams had solved it at the 4 hour mark. Right, next we had problem I, intact intervals. And here we were given a circular array A, and we wanted to figure out how many ways we could separate it into 2 or more intervals. So we wanted to cut this up in some positions, such that some other array B could be obtained by permuting each of these intervals separately, without moving the intervals around. So let's first actually forget that the array is circular and see how to solve the non-circular case, where this is just like a normal array, and we want to figure out how many ways can I chop it up into intervals such that B can be obtained by permuting the intervals separately. Just some notation, let capital A of I be like the prefix of the first I values of this array A, and let S be the number of indices from 1 up to n, such that the prefix of the first I things in A is a permutation of the first I things in B. Okay, so then the answer is simply, in this case, is simply going to be 2 to the s minus 1. And the reason is that breaking up A at any non-empty subsets of these indices is going to result in a valid separation. So there are 2 to the s subsets of these indices. There's one which is empty, which you have to subtract. So there are 2 to the s minus 1 non-empty subsets, and picking any of these and chopping the array at these will lead to a valid separation. And simultaneously, if you break up the array at any other index, is going to result in an invalid separation, because the left half is not, you're never going to be able to make it work, because in the left half there is the multiset of elements that is in the A array differs from the multiset of elements in the B array. So then there's not going to be any way to fix it. So you need to only use these types of indices that satisfy this property, and you can use any non-empty subset of them. So, okay, then we have to just find this number s quickly. And to do that, there are different ways of doing it, but one way which is useful for solving the actual problem in the next slide is to use a permutation invariant hash function. So like a hash function on strings that doesn't change when you reorder the string, when you permute the strings. And this simplest way of doing this is as follows. For each array value x, assign some random hash value h of x, and define the hash h of ai of a prefix to be the sum of the h of aj for the different characters that appear, the first I characters that appear in the string a. Or not characters, these were numbers, but so the first I numbers. And then, assuming this hash function is nice and we don't have any hash collisions, these first I characters of A is a permutation of the first I characters of B, if and only if they have these two prefixes have the same hash value. And these hash values are easy to compute. very quickly. We just compute them from left to right. So that's how to solve the non-circular case. Now we needed to do the circular case, and we're going to build on this solution. So here's what we'll do. For any hash value z, let s of c be the number of indices between 0 and n-1, such that the hash of the first I characters of I symbols of A minus the hash of the first I symbols of B equals z. So all of the positions where the hash value between the two prefixes differs by z. Then, again assuming that we don't have any hash collisions, the number of ways that the thing can be separated equals the sum over all z of 2 to the s of z minus 1. And what is this? The reason for this is that for every hash value z, taking any subset of at least 2 out of the s of c indices will result in a valid separation. So there are 2 to the s of c subsets in total. One of them is empty. S of c of them use only one item, so we have to remove those. But the remaining 2 to the s of c minus s of c minus 1 subsets will result in a valid separation. And in a similar way as before, if you take two indices that have different values of this difference of the hash functions, this is going to give an invalid separation, which is something like both of these claims are something that you can convince yourself of. I'm not going to explain exactly why it is true right now. But this then results in a linear time O of n solution. At least we have to do something like counting how many times did I see this particular hash value z. So this assumes you have some kind of hash tables or some constant time dictionaries that you can use to store these frequencies. So the statistics here were that this was solved shortly before the 2-hour mark, and at the 4-hour mark there were still only 5 accepted solutions. So pretty hard problem, not a lot of teams solved it. All right, we now have the last 3 problems. First of those last 3 is problem B, breaking bars. Here we got a list of rectangular chocolate bars, and we wanted to make as few breaks as possible to produce 2 equal collections of bars, each of those collections having at least t squares. So this problem had a lot of incorrect submissions, and I think most of those incorrect submissions were based on the following incorrect solution, which I'll now describe because it is useful even though it's incorrect. So suppose we're trying to partition all of the chocolate. We're trying to break it up so that we have 2 equal collections consisting of all of the chocolate. So what we do is first we check how many bars are there of each bar size, and we note that there are actually only 21 different possible sizes of bars. There's 1 by 1, 2 by 1, 2 by 2, and so on. And the fact that 1 by 2 is the same as 2 by 1 means that there are not 36 different sizes, but only 21 different sizes. And now, like, here's the incorrect thing, which is to always greedily pair up bars so that you never have 2 or more of any size. To say that, well, if I have 2 bars of the same size, well, they're already of the same size, you know, they're already perfect. I'll just put them aside. I'll use those in my collection. But and then if you do this, you only have 0 or 1 left of every size, and now you can try to find the minimum number of breaks needed for these remaining bars, which can be computed pretty efficiently using dynamic programming over 2 to the 21 sites, 2 to the 21 states. And the reason that it's 2 to the 21 is now exactly this property that you only have 0 or 1 of each size. So there are 2 to the 21 possible configurations of how many bars do I have of each size. And this is unfortunately wrong. So here is an example where this is wrong. Suppose you have these sizes, 3 by 2, 3 by 3, 1 by 5, 2 by 5, and then you have 2 3 by 5 bars. Like this greedy solution would say, I'm just gonna put those aside. Those are already matched. I'm gonna match up those together. This is a bad idea because the optimal solution here is to split one of these 3x5s into 3x2 plus 3x3, and the other one as 1x5 plus 2x5. And then using only 2 splits, we managed to make 2 identical collections of bars of all of the things. So this is a counterexample to why this greedy assumption in step 2 here is actually wrong. So, however, even though this was wrong, it's useful because it gives an upper bound on the maximum possible number of breaks that may be needed. You can use this incorrect greedy approach and some calculation, like you can implement it and check, and you can figure out that you will never ever need more than 9 breaks to partition all of the chocolate. And that's very useful. Like having that kind of upper bound is very useful because that makes some kind of branch and bound solution more viable. And that's what the actual solution is. We kind of recursively search for the best way to break the bars, going from larger bars to smaller ones. And we keep track of how many breaks we have already made and how many squares we still need to partition. And then we avoid doing recursive calls that will produce more breaks than the best solution we have found so far. And we use this property that we never need more than 9 breaks. And we also use the property that any given bar can be broken in a very small number of ways. There are at most 5 different ways of breaking any given bar. And because of these bounds, this kind of branch and bound turns out to be fast enough. Right, so I see there's a comment. There are ways of solving it which are not exactly branch and bound. There are other ways of solving this as well, which we found out because you solved it during the contest in another way. So that was it was very interesting to see. But this was the way we solved it. All right. So yeah, this problem was solved pretty early, after an hour or so, but this was at the 4-hour mark, this was still the only accepted solution, so this was pretty hard. Moving on to the second last problem, Eavesdropper evasion. Here we had a bunch of messages and messages. We wanted to send them as fast as possible, and they were different lengths, but we wanted at most 2 of them to be fully sent within any given, within any time frame of length x. So no matter where you put a little window of length x time steps, there were allowed to be at most 2 messages completely contained in that window. So here's the solution. The first thing is to note that if you have messages that are longer than x, you can basically ignore them because they can never be intercepted. They could never be fully contained in a window of length x. Or you can mostly ignore them because you still have to remember that the final result cannot be smaller than the longest message. So you still have to take a max at the end with the length of the longest message. So, but in principle, we can think of these as not. We can assume that you only have messages that are of length x and shorter. So we'll start by figuring out how to solve a simpler problem where we can have at most 1 message intercepted in each window, and then we'll see how this solution generalizes to 2 intercepted messages. So here's how to do the simpler case where in every window of length x we can have at most 1 intercepted message, or 1 message fully contained. And the observation is that if you have some message, regardless of how long that message is, still at most x, and if that starts at time a, the next message after that can start no earlier than at time a plus x plus 1 minus t, where t is the length of that next message. Because if it starts at 1 time step earlier at time a plus x minus t, without the plus 1, then both of these 2 messages will be contained in the window from time a to time a plus x. So, and that's not allowed. So the next message, if the next message that we send has length t, you cannot start it any earlier than a plus x plus 1 minus t. And if you repeat this and like work out what happens, the total time to send all of the n messages becomes x plus 1 plus the sum from 2 to n minus 1 of x plus 1 minus ti, where ti is the length of the ith message that you send. So like for every message that you send, like the time increases by something which is like x plus 1 minus the length of the message, like the start time. So the total time to send all n messages becomes this quantity. And one thing to note is that the length of the first and the last message doesn't affect the sending time in this. It's this quantity. The ti's only show up for I from 2 to n minus 1. The length of the first and last messages are irrelevant here. So that means that what we should do to get an optimal solution is simply to place the two shortest messages first and last, and then what we do in the middle actually doesn't matter. The order of we do things in the middle doesn't matter. As long as we put the two shortest messages first and last, we get an optimal solution. So the answer is simply going to be the sum x plus 1 plus this sum, where we take the n minus 2 longest messages. All right, so that's pretty simple. So let's then see what happens if we're doing at most 2 messages. And the key observation for the 2 message case is that we can actually view this instead as having like 2 separate channels, and we want at most 1 intercepted message in each of these 2 channels. It's not immediately obvious why this is true, but it's kind of intuitively makes sense, and you can prove that this is indeed the case. So so the only thing that we really have to decide, we already know how to solve the case of 1 intercepted message for a channel. So the only thing now is that we have 2 channels, and we have to decide which messages to send on which of those 2 channels. And if we have some channel where we put our messages of length t1 up to tr, then what we said in the previous case was that this will finish in time x plus 1 plus the sum of x plus 1 minus ti from 2 up to r minus 1. So similarly to the last case, now we should take the four shortest messages and just put them first and last in each channel. That's because those are not going, the things we put first and last in each channel is not going to affect the total send time. So we'll put the 4 shortest messages there. And then each remaining message that we didn't put first and last, we can think of this as having a weight, which is x plus 1 minus t. It's how much it contributes to the total send time. So what we have now are n minus 4, let's call it m equals n minus 4 weights, w1 up to wm. These have some total weight, capital W, which is the sum of w1 up to, this should be a wm, not n, but total weight capital W. And what we want is, we want to find some subset of these messages such that the sum of the weights in this subset is as close as possible to capital W over 2. We would like these we would like to balance these 2 channels so that they take roughly the same amount of time. Because if we put the subset S on the first channel, it will take x plus 1 plus the sum, and then the second channel will take x plus 1 plus the sum of the other things. So we want to balance these things, and this is really like a subset sum or knapsack problem. Subset sum or knapsack. It's something that has a classic dynamic programming algorithm which solves it in time n times this capital W, but this capital W could be as large as n times x. So this is really an n squared times x algorithm, which is way too slow for this problem. However, there is actually an n times x problem for solving these knapsack problems. So what we have is we have m or n items, and the weight, no item has weight larger than x. And in this setting, you can solve the subset sum or knapsack problem in n times x time. And this is an algorithm by Pissinger, who is actually a Danish scientist, a Danish professor at DTU, I believe. So this is a Nordic algorithm, which I actually was not aware of earlier, even though I should have been. But it's a nice clean dynamic programming algorithm, which is pretty. So if you haven't seen this algorithm before, it's a nice algorithm to learn. And so yeah, this one was not solved before the 4-hour mark. There were 19 submissions, so people were trying to solve it, and we'll see shortly if anyone actually succeeded in the last hour. Last problem, last but not least, is the problem M, Marvelous Marathon. So here the goal was to find a path of length x in a 2x m grid under some constraints how this path should look like, and we want the sum of the values in the cells that we visited to be maximized. So maybe a more precise formulation of the problem or a more mathematical formulation of the problem is useful for talking about it. So one can think of the problem as being the following. We want to find integers a, b, c, and d between 0 and m, which represent the turning points we make in this grid. So here is the path from the sample in the problem statement, and the a, b, c, and d would be these points. So we start at point C, we go all the way to point D and make a U-turn and go back all the way to point A, make a U-turn and end up at point B. So we want to find these 4 key points A, B, C, D, such that 2 times B minus A, which is these 4 squares, plus C minus B, which is this interval between from B to C, plus 2 times D minus C, which is these 6 squares, should be equal to X, the total length of the path. And then what we want to do is want to maximize the sum of the cells in one of the rows from all the way from A up to D. So all of these cells in this row, plus the sum of the cells in the other row from A to B and from C to D. So this is one way to view the problem, and so an obvious trivial algorithm here is to solve is an m to the 4 time algorithm by just trying all possible values of a, b, c, and d. But this is going to be horrendously slow because this m was as large as 1 billion. So you basically don't even have time to try 2 of these, much less all 4 of them. Right, so this m is very large, so we cannot really loop over all cells to find these points a, b, c, d. But this grid is very monotonous. Like it was defined by these intervals having the same values. So there was an interval all the way from here up to here with value 7, and one from here to here with value 9, and so on. And there were only a small number, like 200 of these segments. So like large parts of the grid kind of look the same. And that's what we're going to use. And we're also going to basically separately handle 3 different main cases, having either 0 U-turns, 1 U-turn, or 2 U-turns. So this example down here is the most general, with having 2 U-turns. But it's convenient when solving this to deal with these cases separately. And in these slides, I'm just going to focus on the hardest case with 2 U-turns, because if one can solve that, like solving 0 and 1 U-turns is just simpler. Okay, so then first insight that, or some insights that we want to make. First, we can assume that the solution has the gap in the lower half. So as opposed to this picture has the gap in the upper half. But we can assume that the solution has the gap in the lower half because we can, if we have a solution which solves that case, we can just flip the top and the bottom row of this grid and to cover the other case. So we can assume that the gap is going to be in the lower half. Actually, let's assume that it's in the upper half because that's what it is in the picture. And now there is an optimal solution where either of these two like extreme points A and D is at some segment endpoint, or at 0 or M. Because if there wasn't, we could kind of move things around. We could move like A and D to the left, like in tandem, or to the right in tandem. And this would keep increasing or keep decreasing the total score until either A or D reaches a segment endpoint, or like D collides with C or A collides with B. But when that happens, we have basically gotten down to the one U-turn case, which we kind of already handled separately, and we imagine we have already solved that. So we can assume that A or D is at an endpoint of one of these n segments, and we can actually assume that we can actually assume that the one that is at an endpoint is A and not D, because again, by symmetry, if we run the whole algorithm on the reverse of the grid, we flip left and right, then D and A switch roles. So we can from now on we can assume that this point A is actually at an endpoint of one of the intervals in the input. Second insight, we can do the same thing with B and C. We can assume that either B or C is at an endpoint of one of the intervals in input. Like in this picture, both B and C are actually at an endpoint like this, because there were the 4 switches between to 0 and where the 0 switches to 6 here. But we can, in general, assume that at least one of them are. For the same reason as before, we could move them left or right in tandem, and the score would increase or decrease linearly until one of them hits an endpoint. So we can assume that B or C is at an endpoint. So now we have two cases to consider, like either A and B are both at segment endpoints, or A and C are both at segment endpoints. These are again two cases that you have to deal with, or that at least our solutions have to deal with in the code. And to make this presentation not go on forever, let's focus on the first of these and assume that deal with the case when A and B are both at segment endpoints. You also have to solve the other case, but the way to do it is very similar. So here is how to do that. So we know that A and B are at some segment endpoints. So let's fix which endpoints they are. There are n squared possible choices. And then we set C to be the same as B, and D to be basically this A plus x over 2. So that way we start there. That way we have a race, or like a path, which has the length x, which is kind of where D is as small as possible for these given values of A and B. And then the idea is to keep A and B fixed and slide C and D towards the right, like rolling it towards the right, where C will move twice as fast as D, and we maintain the current score of the path as we do so. And the point is that since these grid values rarely change value, because there are these few interval key points where they change value, we can slide large distances at a time. And what we can do is we can quickly calculate when either C or D is going to hit the next segment endpoint and just jump straight there. And we repeat this until until D reaches the end of the road. So this next segment endpoint can be found in constant time, which is going to lead then to a total time complexity of big O of n cubed, because there were n squared choices of A and B, and then there's basically n different key interesting steps where to consider for how C and D are configured. So this is this was how to solve a special case of the problem, and there were lots of cases I didn't cover. So the implementation for this problem is quite a bit of a mess, and like all of the judge solutions are quite long for this problem. So it takes some effort to implement. And while this is n cubed, I will say that it's probably possible, or we know it's possible to get an optimized n to the 4 time implementation to pass as well, though it's not that much easier to implement, because like most of the implementation difficulty is not in making this last step fast, but just in the general setup of everything. But it was possible with some effort to also make an n to the 4 pass, but the intended time complexity is n cubed. And at the 4-hour mark, there were 0 submissions and 0 accepted solutions for this. There were some submissions in the last hour, so we'll see if anyone managed to crack this little nut. So that's it for the solution presentations, and with that we're gonna switch over to the results. So here is what the scoreboard looked like at the 4th hour. We had Umogen Heap from KTH in the top, closely followed by the Taste Code brothers from Copenhagen, both of these two teams at 10 solved. And both of them made efforts to solve more problems in the last hour, which are indicated by yellow in this little table. So we'll see if any of them succeeded and if any of the teams further down in the scoreboard managed to catch up. But first we'll do this, we'll start going down and see the rest of the scoreboard. So let's see, there are around 200 teams which we have to scroll our way through. And a lot of submissions happening in the last hour that we will now see how how many of them actually passed. Right, so we have a few teams which didn't solve anything. Let's see if I can get this. We have Altosyl, which tried a few things in the last hour, and they got their first problem with 11 minutes left of the contest. Great work. Academics Quart, they managed to get something in the last hour. Taltech also gotten their third problem. Tob Push proved Gandalf wrong, tried a lot of things. Most things seemed to fail, but they did get something, so moving up. It's always worth trying. Omega N squared moving up. Ducati moving up. Embedded Boys moving up. Bobby Tables. Dat Uno getting another one. Prove Gandalf wrong. They had even two of them. GCD. I can't pronounce that. Vilnius Tech. Honey Badgers. Webbase. Norwegian Salmon is out. Gutta getting another one. Fibonacci. Also Java Bra getting another one. Not P-Space. P apparently is now equal to P-Space. This is news to me. Gunners, Java Beginners. BlueJ dropped database. Dropped all the databases. EPMP, Poikene från Norr, Beat Soccer, Team Rap, Powerpuff Girls, Good Bad Ugly, Monkey on Typewriters, Sudo RM removed all their errors, Vilnius Tech, Embedded Boys. Gandalf is now finally done, but they did get some things in the last hour. Great. TTU winners, 2.5 Danes. IQ equals max value. Was not enough IQ, maybe. Gobbles, placeholder lognamn. Snakes. Programmerbar. Noragang. Control Alt Elite solves another problem. Team ESA solves another problem. But honest work. O of n factorial was too slow. O of x by n factorial was surprisingly fast enough. Suits Hatifnattarna, Bogosort, Pollard's B-Rose, got another problem. No good game, no good name. Seniors, done. Oh, no Factorial. Also did not get their last. Bold, Loneliness, Discode V2, DT Winners, Control Alt Elite, Team ESA, Programmerbar, Norgang, Expo Factorial. This time it was too slow. Visit from Bergen, no, Deep Thought, nope. Ich verstehe nur Bahnhof. From Aarhus, Import Matamalog, Spaghetti Banden, Sigma Bulls, works on my subsystem. Well, Skalgomen, P-Space Invaders, stuck in P-Space, Dream Team, Living the Dream, Högre Väsen are done. Huh! Also done. TMP, temporarily out of problems. Past our prime, going up. Millennial Falcon going up. Pray for Igor going up. Noobs at LTH. Dream Team, done. KTH, Skalgomen, and square root of -1, also done. VA Enthusiast, Max Min Age are done. Past our prime, are past their prime. D++ from University of Iceland, we briefly paused there because D++ are the Icelandic student champions this year, the best ICPC eligible team from Iceland. Moving on up, Kommandorörelsen, out of commands, Tarzan, Fredrik's Minions, moving up. Hope it passes, moving up. 99 bugs on the wall, everyone's moving up, everyone's solving problems. Ballondyrene, getting up. And Fatal Error, trying C, getting it. 1-1 Pulse, failing on E. Fredrik's Minions are done, hope it passes. Library of Babel, moving on up. Ballondyrene again getting a second problem, moving to 17th place. Fatal Error moving to 16th place. Pragerkribben are done. Balloon Wizards are done. Förvera försteklassinger. Rainbow Unicode characters getting C and moving up. Temporary out of problems. Beyond Balmer's Peak Union Frexen moving on up. Library of Babel are done. Fatal Error are done. Förvera försteklassinger are also done, but we pause here because Förvera försteklassinger is the Norwegian student champions, the best ICPC eligible team from Norway. Congratulations, well done. All right, and now we are in the top 20 at 8 problems solved. Algo UB are done, Rainbow Unicode characters are done, Scream and Cout, SP3D V12 moving up, Balmer's Peak moving up, reaching that peak, Ace of Spades are done, Mangolassi Fan Club are also done, and here we pause because Mangolassi Fan Club are the Finnish student champions. Great job, guys. So at 14th place with 8 problems solved. Then we have the 5 engineer. Actually, this is the 5 euro engineers because this program cannot show UTF-8, but it's imagine a euro sign between the 5 and the E. So the 5 euro engineers from Vilnius University are the Lithuanian student champions. At 8 problems solved, 13th place overall. Great job. Then we have the inverse exclamation points are done. Two Gamlir are done, not done. They're moving up to 8th place. Cyan Forces, trying B, failing, C getting. Balmer's Peak are done. Now we're at SP3D version 1.2, Spratus Spratus from the University of Tartu, which at 9 problems solved are the Estonian student champions. And 10th place overall. Great work. Very nice. Next we have the two Gamlia, which are done, so they end up at 9th place. Cyan Forces still have some attempts on problem I, and in the last minute, so let's see if they manage to get it and move up. Nope, unfortunately, that's it for Cyan Forces, which end up in 8th place. Then we have the expected rank tending to infinity from University of Helsinki, which had submissions for both problems E and I. So let's see what's happening with problem E, if they pass it or not. And no, they did not get that one. For problem I, let's see if they get it. They do get it, and they move up to third place. Then we have ECPC from Lund University, which have submissions on both C and M. So let's see if they get the one on problem C. And they get it, moving up to third place. The fight for the first place is tightening. And now we have the floor is made of Java from Danish Technical University of Denmark. They only have submissions on problem B made in the last minute, so we'll see how this goes. And unfortunately, that's it for the floor is made of Java, and we still stop there because these are the Danish student champions at 7th place overall with 9 problems solved. Cool. Excellent work. All right. Next we have Vimsalabim from Chalmers, which have submissions on as many as 3 problems, so they could reach 12 problems solved. Let's see how they do on problem B to start. And it's not a pass, so, well, still have 2 more problems. So on problem C, they do get problem C and move up to 5th place. The chick, the duck, and the goose. Let's see, they have submissions on problem H, and they get it. Moving up to 5th place, taking it back from Vimsalabim, who now have to counter with their submissions to problem E, and we'll see how that goes. Anas, that was not a pass, so Vimsalabim are stuck at 6th place. Still an impressive achievement with 10 problems solved. The chick, the duck, and the goose are done, getting 5th place with their 10 problems. The expected rank tending to infinity is also done, getting 4th place with their 10 problems. And this is actually a one-person team, so really impressive to solve 10 problems with just one person. And you know, if this was a 3-person team, they would have solved 3 times as many problems probably. So they would have won the contest easily. So very gracious of you to compete alone to live so that the contest was fair. Well, moving up to the 3rd place, we currently have ECPC, which are have only submissions on problem M left. And let's see how they do. And they were the only team to attempt this problem in the entire contest. So really hope they get it. But unfortunately, they did not get it. And they are at 3rd place. And that means that ECPC are the Swedish student champions. And actually they are the Nordic student champions as well. They are the best ICPC eligible team in the contest, getting 3rd place with 10 problems solved. Next, we have the fight for 1st place with 2 teams left. It comes down to Umugun Heap versus the Taste Code Brothers, KTH versus Copenhagen. So let's see how the Taste Code Brothers are doing. They have submissions on problem E, so they need to get this in order to pass Umugun Heap. And let's see, they did not get problem E. So that means that they are the 2nd place team, and the winners we know now are going to be Umugun Heap, but let's see what happens with their last submissions, and let's see if they could get another problem and solve and get up to 11 or 12 even problems. So they have submissions on problem B, which so far was only solved by expected rank to infinity. That's the only team so far that solved it. And they didn't get it. So problem B remains solved by a single team, expected rank to infinity. Last, they have problem E, which no team solved so far. None of the teams actually solved problem E so far. And they have a lot of attempts, which is usually not a good sign, but let's see. They do manage to get problem E, reaching 11 problems, and being ahead of the second place by one problem, and cementing their position as the Nordic champions for this year. So yeah, that's Umogen Heap, Nordic champions for NCPC 2021. And great work. Really impressive that you solved most of our hard problems. Only problem M remained unsolved, and yeah, that is all for today. I hope that many of you will consider going on to NWork, which takes place in November, not in Iceland but remotely from Iceland. And yeah, thank you for joining us today, and have a nice continued weekend. Goodbye.